And this does not work. So this is work done as a part of the brand new gravitational physics group at ETH, also known as the Vallisneri group. I don't see him in the room, but he would be happy that his name is up here. But more specifically, this is work done as a part of DP-CACH, which is the Swiss LISA Data Processing Center, which I manage. You can see we have a lot of lovely people that are part of DP-CACH, some of them also in the room. But really, everyone that is a part of the Vallisneri group is also contributing to DP-CACH, and most notably Pat Myers, who's my co-author on this. So I'm sure you've heard there are galactic binaries in our galaxy, and most importantly in the LISA data. We expect around 10 million galactic binaries to populate the Milky Way, mostly double white dwarfs, and some small fraction of those, maybe roughly 1,000 per year, should be resolvable within the LISA data. So the vast majority of those sources builds up some confusion background in the LISA data. And we have several examples of populations that we should expect. Here's a non-comprehensive list. And in particular, this plot that I'm showing you right now is an example catalog courtesy of Astrid Lamberts and Alexandra Tubiana, and it's very similar to what is in the LISA common data set that many of you have either already been analyzing or will receive soon. So as I said, some of those signals will be resolved, and actually as you resolve them, you're picking them out of the data stream and you're subtracting them from the confusion noise. So as LISA observes, you resolve some signals on one side, and your estimate of the noise from the galactic binaries changes on the other side. And this little simulation is powered by GB Confusion, which is a package that our student Alice released as a part of the DP-CACH GitHub, and it's based on the subtraction algorithm Karnezis et al. That I think many of you already know. So how do we leverage this relationship within a global fit? So if these two sides, the resolvable sources and the confusion background, are expressions of the same population, we can leverage them to learn more and to actually have a handle on the global fit convergence within actually the parameter inference itself. So the sources inform on one side what background or what confusion foreground I can expect, and the confusion foreground itself also informs and actually limits through the noise estimate what sources I should be able to resolve. Now I wanted to put this disclaimer up right up front. I know I'm in a background panel, but I'm not so much interested, in the population inference side of this project. What I'm most interested in is to have some independent noise estimate, independent from, let's say, the noise estimate from the data from the noise brick that goes into the global fit and can provide extra information and hopefully catalyze the convergence of the fit itself. Now, I've said global fit a bunch of times, and I realize Tyson's talk is like tomorrow or Thursday, so just to make sure everyone's on the same page, we're doing a global fit of the LISA data. What that means is we're analyzing the entire data set at once with a single likelihood, with one big template that is the sum of all the possible signals that we expect to see in LISA. What that means is different source types, so some over different types of sources, but also some over all the different numbers of sources that comprise the population that we're fitting for. And that number of sources is actually an unknown. So the challenges here are, of course, this is a template that is expensive to calculate. It's hard to find the maximum, global maximum of this likelihood. But the unknown number of sources is also a pain, and it's especially a pain for the galactic binaries. So this is where we're inserting ourselves in terms of the new HBGBs project. Now, the global fit is clearly a huge sampling. Oh God, something vibrated. No, okay. It's clearly a huge sampling feat, and there are ways of dealing with that if you can assume that to some extent the sources can be sampled independently, so that's where this blocked Gibbs approach comes in. I'm sure you're going to hear a lot about that tomorrow. But in terms of the dimensionality, so the variable number of sources that we're fitting for, there are different approaches there as well. So one thing you can do is reversible jump MCMCs. Several of the current global fit pipelines are based on that. Or you could do something that is very similar. You could sample product space. I'll be talking about that in just a minute, but just so you know, formally there shouldn't be really any differences in terms of the output. It's just a different way of running your sampling in the, within the likelihood. So I'm taking the opportunity, oh, this is annoying, isn't it? Well, okay. I'm taking the opportunity to advertise what we're doing within DP Catch, and I'll be talking about HBGBs, so this joint estimation of the sources and the foreground. But there's actually another approach that we're developing in DP Catch as well that's actually a simulation-based inference search and amortized inference approach called slot flow. So the reason I'm putting it up there is, first of all, I want you to Google slot flow, Niklas Hube and Giovanni Giarda, and find out sort of just how great their software is, but also because I'll be comparing against their code base. So in a nutshell, what HBGBs does is we have some expected number of resolved sources informed by a population model. We sample around this expectation value to then sift through the data in product space to sample the source parameters. That through this, we are able to update our population model from the data directly within this global fit framework, but at the same time, the population model also informs the noise estimate. So all of that is coming together within the same framework. That's a lot to handle, so I'm gonna start by talking about the individual sources, how we deal with that, and that's what the Gaussian likelihood looks like in product space. It's just a Gaussian residual likelihood, but you see that I've rewritten it to highlight these inner products, the dimensions of which are fixed to some maximum number of resolvable sources that I can expect. So differently from RJMCMC, where the dimensions of the inner products are variable, this is a fixed dimensionality, but which parts of that inner product are actually relevant is regulated by an indicator vector, or vector of indicators zk, and zk are variables that can be either 1 or 0. 1, the source is relevant, I'm actually tracking it in the data. 0, it's irrelevant. I'm sampling its parameters, but they're really not meaningful, and I'm not keeping track of that signal. And the indicators are updated based upon, well, first of all, the probability of a source being in the data through the matched filter. So this is just the parameters of the source make sense. Does this match the data at all? But it also depends on population relevant quantities. So for example, how many other sources are on in the data at that given time? So that is regulated through the number of resolvable sources, which is drawn from an expectation value of the number of resolvable sources that comes from the population. So, sorry, it's so much easier if I can point. So this is really the heart of the first half of HBGBs, is the relationship between the expected number of resolvable sources and the population, right? So it's the integral over the entire population thresholded by some resolvability threshold choice. Now, disclaimer that is really important to highlight here, HBGBs is not a search algorithm. It is a parameter estimation algorithm. We start around true values. We assume that some search has been performed. That's not gonna happen. Okay, it's not gonna happen. We started really late and I had lots of technical problems. Yeah, it's not gonna happen. Give me 3 minutes to 12 minutes? Yeah, that's 5 minutes then. You can ask me questions when we get coffee. So this is what the inference looks like for a simplified in a simplified data set with 5 sources and no confusion noise. Here we're using galactic binary templates from JAX-GB, so full parameter space for individual binaries. That's what our inference looked like. This is just a proof of concept that sort of we know how to sample galactic binaries, and it compares quite well with slot flow. So as I said earlier, I wanted to add that in. Note that slot flow performs a little bit worse, or is a little bit less stringent around the parameters, and that's just because it's also doing a search step, okay? So I would say this is a good proof of method for both packages. So in the interest of time, I'm gonna speed up and sort of talk about the other half of HBGBs, which is the population component. And the other half is regulated by the other half of that integral. So the number of resolvable sources depends on the portion of the population that passes a resolvability threshold. The other half, the one that doesn't pass, builds up the confusion noise, and that's what I'm highlighting here. So the expected number of resolved sources, the expected confusion foreground, and also the entire integral, so the total number of sources, are deterministically related in terms of expectation values. Now, so what you have to add in is, of course, some uncertainty around that expectation, which may be Gaussian if you're in a large numbers limit. We actually don't take that limit. We actually train a neural network and emulate the probability distribution of the confusion noise directly. So just trust me, at this point, it's being taken into account. And there's lots of similar approaches out there, okay? So we're all talking to each other, and we're all coming up with different solutions to this problem. So here's an example of HBGBs working on a narrow frequency band with a simplified waveform of 2 parameters. So here we have amplitude and frequency. All of the other galactic binary parameters are fixed. This is a narrow band with 200 sources. I would say successfully estimate the total number of sources. This is our population parameter that we're not keeping fixed. We're actually inferring within the data. And it does an okay job estimating the confusion noise, and it does a good job at estimating the 15 resolvable sources, or it does a good job in finding, I would say, 15 resolvable sources in this data set. Maybe you'd have to squint, but you can see that the sort of injected and recovered values overlap, and actually the posteriors look really nice. It does find a couple extra sources, and I think this is related to the fact that it overestimates the confusion noise, it overestimates the total number of sources, and so it tries to squeeze a couple extra sources in there. We're working on finessing this. It doesn't happen at every iteration and not in every chain, so this is really a sampling game. And long story short, I would say cataloging approaches, cataloging cuts are actually going to come in here and tell you what to do with these threshold sources. So conclusion remarks, where do we go from here? I just showed you a proof of principle in a single narrow frequency band. But really the idea of HBGBs is to do a Gibbs within Gibbs across frequency bands, tracking population level parameters across bands, and then in each individual band you do what I just described. I would say we're here in terms of implementation, and right now we're running this implementation, which has each band communicate given some global population, which includes a global confusion noise model and a global population model. And I'm going to stop because I've run out of time, right?
Thank you very much. Great talk. Questions?
Really nice talk, Arianna. I was really interested that you were using product-based sampling, because we've used that quite a bit in PTAs over the last while. And the issue is usually one of sampling health when you've got quite disjoint models. So I'm wondering, have you noticed that the chain takes a while to recover whenever you're adding many new parameters? Like when certain sources become inactive, you're then basically sampling from the prior and have to lock back on again when it becomes active?
So lots of technicalities there. TLDR, it's very hard to resuscitate one of those guys. They jump around a little bit, actually. So they do jump from, let's say, one source to the next. So the Bernoulli prior that impinges on the ZKs, on the indicator variables, is informed by the expected number of resolved sources. So if you're doing a really bad job and you think you should be resolving more, it does switch them on. So my next step is going to be, where does it switch them on? Right now, it just switches them on in random places in the narrow band. It is such a narrow band that it might happen right around the right place, but it's such a peaky. It's such a peaky likelihood that if you miss it, you miss it, right? It's very hard to find it. So it's going to be the relationship between searches and the sampling that I think is going to be the answer. Maybe pseudo priors,
okay,
which is what we're
thinking about.
Yeah,
that'll be very interesting. We should talk later.
So when we take the next question, could Iuliu Cuceu please start preparing? As I understand, the next speaker cannot talk now, so please, thank you.
Thank you. Just could you say a little bit more about how you set the detection threshold and how your results depend on that?
So the detection threshold is an SNR threshold. And it's actually, so this is actually why I had this in there, which I quite like. So I would say we use exactly the same approach that is used in the subtraction, sort of the best case scenario subtraction algorithm that is used here. The exact same algorithm is used to train the emulator that learns basically where should the detected and undetected sources live in parameter space. And it is an entirely, it's just a choice, right? It's a choice that we make in the training, and then it's a choice that we remake when we run the search. And as long as that choice is consistent, right, that should be conserved. But it's entirely an SNR threshold.
Okay, let's thank Arianna again. Thank you very much.
Hi, thank you. I'm Iuliu. I work at the Observatoire Côte d'Azur in Nice, France. And I'm going to talk to you today about stochastics with machine learning, and I'll try really hard to make the machine learning part very simple and very quick, because I know you care about the physics. Yeah, so stochastics. No, still doesn't work? Okay, later stochastics. Okay, I'm going to stop saying stochastics, I think. I'm sorry. So what's the point? I think if you're all in a stochastic session, I hope you know by now that there's a lot of different kinds of stochastic components superimposed in the LISA data. At the minimum, just like in the LVK, you have instrument noise, but you also have a big galactic foreground in the way, and those are the things that we're certain will be there, and probably many other friends, such as cosmological, that's a holy grail, extragalactic white dwarf, EMRIs, some astrophysical component, and this will all happen in the presence of non-Gaussianities. Here specifically, I'll be talking a lot about glitches, but also data gaps, every other source, essentially in the way. So the question is then, how do you do, that green line is not mine, how do you do robust stochastic component separation in the presence of non-Gaussianities, and quickly? So the setup is very simple. Essentially, we try our best to parameterize. We care about the signal, so we parameterize the signal, and we try to have as flexible as possible noise. So in this case, parameterize galactic foreground, parameterize stochastic gravitational background, and a semi-parametric, which means splines in practice, TM and OMS noise. And all of this combines in 11.6 days of data, mainly chosen because of stationarity of galactic foreground. So we don't have to deal with stationarities, non-stationarities. And on top of that, we put glitches in. And we end up with a full data periodogram, and all of this analysis will work on that entire XYZ data periodogram, 3 by 3 times a coarse-grained, so from the 11.6 days resolution, frequency resolution, down to about 500 frequency bins. So the framework is not quite Bayesian, but almost. Simulation-based inference. Generally, the difference is that you start with draws from your prior, and you just say that you don't necessarily need to be able to write an analytic likelihood, you just are able to construct your data from those parameters, e.g. by composing different sources. And having draws from that prior and your simulator, you can then train a network that estimates your posterior, and maybe it might even be right. That's not what I'm doing. That's the general SBI. What I'm doing is a bit different. It's diffusion-based, simulation-based inference, in the fact that I don't actually estimate a posterior, I estimate a score. So essentially, you start with your data, you have an embedder because the data is big, and especially when this will scale, an embedder is a super important part. It's essentially a learned summary statistic. That gets thrown into a transformer whose purpose is to estimate the score, so just the derivative with respect to the parameters of the posterior. And then you have to solve a reverse stochastic differential equation, and you end up with a posterior eventually. And the main general benefits of simulation-based inference, as touted usually, are it's amortized, i.e. it takes much faster than MCMC when you actually have some data. That's not really what I care about right here. I care about here much more that the likelihood does not need to be written down. It's still faster than MCMC, but not as fast as usual SBI methods. And I'm very happy to talk about the ML part later, but I'll go to results. So frequency data. Essentially, we start by composing different stochastic sources. So you start with a spline noise, and in this particular case, both for the TM component and the OMS component, we have 5 different amplitudes as 5 fixed frequencies for splines. This can be modified, and that's kind of the point. And this is in the spirit of non-parametric. You want your noise to eat up the variation that you cannot explain. And you want, in contrast, your signals to be very well defined. In this case, 3 parameter, well, it's 5, 2 are fixed, 3 are free. Parameter galactic foreground. And on top of that, also some stochastic gravitational background component, in this case a 2/3 CBC background. As you've seen so far, everything I've shown is actually posteriors. We'll get to that in a second. But the point here being that we can do component separation. And how does that actually look like in practice, and is it correct? So posteriors are a very interesting thing. In this particular case, we have, since it's 11.6 days of data, if you want to be even remotely realistic, your stochastic gravitational background will be very low SNR. And your galactic confusion foreground is, well, estimated when we compare with MCMC. In this particular case, we could write a likelihood because no glitches just yet. So you can have an MCMC for comparison. In the stochastic gravitational wave background part, because it's considerably lower amplitude, lower SNR, you would only be able in reality to put an upper limit in this particular case, and in that sense they agree. But more importantly, because I really want to focus this entire talk about how do you check posteriors of machine learning, is that you can do, and this is what is done in the LVK, you can do importance sampling on this. If you trust your likelihood, in this particular case you would because it's Gaussian data. If you trust your likelihood, you can just do importance sampling and these two distributions will match absolutely perfectly. That's not a problem. And if anyone cares about noise, it's all the noise parameters that also essentially agree. But let's go to actually weirder likelihoods, and in the case where you don't trust your likelihood necessarily. So as I said earlier, if you just have PSD components, they're Gaussian distributed in the fine frequency resolution. At the coarse frequency resolution, it's a Wishart likelihood that you can write down. It's what's used in the global fit as well. But in my particular case, because I'm interested in, let's say you have a glitch on top, you can also write an explicit likelihood that estimates the glitch parameters. That's a non-central Wishart. And you can also write, if you want, an analytically marginalized, so you marginalize over the glitch parameters likelihood. Both of these likelihoods, one that explicitly estimates the glitch parameters, if you really trust your glitch shape, one that doesn't. We have both the likelihoods, and we have also the networks, two different networks, one that again estimates explicitly the glitch parameters, one that marginalizes implicitly. So what do glitches do? Well, in this case, for observation purposes, I took a much larger galactic foreground, as you can see. But the point is, glitches are very, very annoying, and they build up very quickly. So in this particular case, I'm going to showcase shapelet glitches. It's in only one single TM, so it's only one single satellite. So it will show up preferentially in only X and Y, not in Z channel. So there is information to be learned. In this particular case, it will show up as a rise at low amplitude. This is a low, quote-unquote, 300 SNR glitch. If you go higher, you end up, yeah, that's like the 1,000 SNR glitch, what that looks like. Over like, this is like a 2,000-second glitch. And even more so than much, much higher, such a glitch, you would probably just throw the data away. But I am actually explicitly showing all these three cases because interesting things happen between likelihoods and between doing machine learning when you try to do component separation in such a scenario. So first, for sanity check, can you actually get your galactic posterior, so let's say in this particular case your signal that you're interested about, can you get it out correctly in the presence of glitches? So I'm showing here 4 posteriors and a truth. I'm showing a network that marginalizes over the glitch parameters, also a likelihood that marginalizes over the glitch parameters, similar network and likelihood that explicitly estimate the glitch parameters. So they all pretty much agree. Again, if you like this, you can do importance sampling. But if you move, this is in the case of a very, very low SNR, quote-unquote 300 SNR glitch. If you move to a higher SNR case, things break, and in interesting different ways. So first, at the medium regime, let's say medium 1,000 SNR glitch, the network performs is slightly less confident. And this is a trend I've seen over and over again. Whenever information is not clear, simulation-based inference in general will just be wider, not biased, and that will be important later. So in this particular case, on the left, the likelihoods perform better. Again, if you want, do importance sampling. In the case of a really, really loud glitch, very interestingly, you can still kind of recover something. So in this particular case, the likelihoods break because of numerics. And also I should mention, especially the exact L1 likelihood takes a lot. You would never do this in practice, and it's with one glitch. If you know anything about glitches, with like 4 a day, I'm analyzing 11.6 days of data. If I were to be realistic about this, it would all break. So at the level of analyzing one single glitch, you right now I can write the likelihood. In general, you will not be able to. But point here being that even at a very, very loud SNR, networks still can kind of recover something. And this will be important when you start adding segments together and building SNR over time and moving on to the full data regime and maybe getting a holy grail of a cosmological background. So going back to what I've said over and over again, what importance sampling actually is and does. So this is LVK Dingo framework, essentially. You have some posterior that you get from machine learning method, and you trust your likelihood easier in the LVK. So what you do is if your posterior mostly aligns with the truth, it has enough support for the truth, you can just do importance sampling and you're guaranteed asymptotically to get your correct posterior out. And you have metrics of this, such as sampling efficiency. In this very baby case, it's 25% sampling efficiency, so much more than MCMC with 0, 0, whatever. So the Jensen-Shannon divergence between the 1D marginals goes down with importance sampling as it gets closer to the truth. But this is if you trust your likelihood. If you do not trust your likelihood, you do what usually is done in the case of SBI, which is population level checks. In this particular case, you have PP plots, as I'm sure you've seen before if you've ever seen an SBI talk, because that's what usually people show. I will put a caveat that the vast majority of SBI checks, 1, their population, 2, they are necessary conditions for posterior calibration, not sufficient conditions, with some caveats around that. You can do fancier stuff. But for the most part, it's really, really hard to know that your posterior is correct when you have little to no likelihood information. If you have likelihood information, as I said, and you're willing to spend the compute, it's doable. But yeah, we are calibrated in every network. I've actually shown 3 different networks so far. Every network is calibrated at the population level. Per parameter, weirder things happen. Essentially, at the level, so the cyan and yellow plots, yellow dots are the galaxy and the stochastic gravitational background. Both are calibrated with one falling a bit. So if the p-value is very, very low, it is miscalibrated, it's overconfident in practice. Sorry, underconfident. What I want to say mainly is that the spline parameters, the noise you don't really care about, that is what very consistently eats the variation and miscalibrates the posterior. But this is as much a parametrization, semi-parametrization issue as much as it is an inference kind of issue. So in conclusion, I want to leave you with the message that we can do, SBI can do stochastic component separation in the presence of known Gaussianities. We have posterior checks that partially come from likelihood if you trust it, partially come from population level diagnostics. And this is essentially meant to be a framework, and will become in the future, a framework for active noise estimation in a pre-global fit sense kind of search. The purpose is that this will have to deal with another 2 things that are big. One is data gaps, but we're moving to time frequency. And then obviously I did one glitch. Yeah, when this has MBHBs and GBs, it will be a problem. But this is aimed at shorter segments, and even 11.6 days, it will be aimed at like hours long segments to deal with the data gaps and the glitches. But yeah, the point is to show that you might want 2 things out of SBI. Maybe you care about speed, but in this particular case, I think it's much more interesting that you can give a good estimate to the global fit earlier on without having any assumptions, essentially. You can marginalize over those sources you're not interested in. Here I'm doing stochastic component separation. Other people, there have been other talks that you've seen maybe today in SBI doing with MBHBs. But it will be a very important part, I think, for anyone that does global fit to have searches that can provide something like this. And how well, we shall see. Anyway, thank you so much for your time, and I'm happy to take any questions.
Very much. Questions? So if I understand correctly, you are considering the situation in which there are several of those glitches, because how long they are?
In this particular case, glitches were like up to a few thousand seconds. In practice, as I said, we expect about, I think, 4 glitches a day, something like that. And that's why the aim is in the future to move this to data segments of like hours long and do multiples. Essentially, so a scheme
Because
like that, where you would have one
in
glitch.
general, I mean, the stochastic signals are there, right? They are
Yes.
there for 4 years, for 10 years, so one would not expect the glitches as such a big deal when you integrate for years, right?
Yes, but the point, as I said, the point is that this is meant to eventually become a quote-unquote active noise estimation, to be provided in real time and also to initiate a global fit. And also because then it can deal with non-stationarities. So it is not directly meant at very, very high sensitivity. So if you want to get the cosmological background out after 4 years, it is not quite yet aimed at that, mainly because dealing with such large amount of data, I don't know how you do it currently today with embedding in a simpler way. I've never seen anyone do it at such like full resolution. That's a different project going in parallel.
Okay, thank you very much. Is there any other question?
Nice talk. Can you comment a bit on how this depends on the particular glitch morphologies?
So from the likelihood kind of sense, the two likelihoods I've shown you, both of them are actually independent of the glitch morphology because you do maximum likelihood search. When you estimate the glitch parameters, you need to know the glitch morphology and be able to parameterize it. From the SBI side, it doesn't matter. That's one of the main reasons why we like SBI is that you can give me any glitch generated that you consider is realistic enough. You do not need to parameterize it for me. You just need to be able to put in the data. We can marginalize over it. I have yet to see that fail. I have not stress tested it, however. I don't know how it will end up in the future. But yeah, in principle, it should work.
Okay. Let's thank him again. Thank you very much. Robert Rosati, please.
Yeah, hi everyone. I'm Robbie Rosati. This is some work I've been doing with Tyson at NASA Marshall, and we've been trying to get ready for the next set of data challenges. So we've been switching our global fits into time frequency domain, wavelet domain, WDM domain. And yeah, so this is the noise and stochastic background sampler that I've developed and integrated into GLASS and Erebor. It's also related to another project I'm doing with some collaborators. Actually, Tina Minkinen is giving a talk in another session, a couple talks after this one, if you want to hear about that. And there's also another kind of review paper of WDM domain I'm working on with a couple of other collaborators. Okay, so as everyone in this room knows, LISA data is not very stationary. It's non-stationary because of the orbits, right? The arm lengths are flexing by a few % throughout the year. There are also non-stationary signals and foregrounds that are happening all the time. The galactic foreground is localized in the galaxy, right? So is only at a certain location in the antenna pattern at any one given time. And when you take all these things into account and simulate very realistic LISA data, like we recently simulated in this Mojito data challenge that's coming out, you see a lot of strange effects. So the nulls in the TDI response, these blue lines wiggle around a little bit as the arm lengths flex. And you can also see on the right panel there, the confusion noise has ups and downs throughout the 2 years of data. So I hope that motivates you to consider that stationarity or non-stationarity, it matters. So you might try to study it. And this is an Emery waveform, but through a few different methods of doing time frequency. There are a lot of different representations out there in the literature. Yeah, there's short time Fourier transforms, continuous wavelet transforms, discrete wavelet transforms. And the one we're actually using is called the WDM transform. It's in the lower right here. It has a lot of nice properties. We can calculate it really quickly from the FFT. So it's same complexity as the FFT algorithm. It's invertible, so there's no issues with things like windowing or needing more or less chunks and more or less data. It's just a total exact transform like the Fourier transform. And we can also choose how much time or frequency resolution we want. And in principle, we should get the same answer kind of no matter what we pick, as long as we fully model the covariance. And the nice thing for noise and stochastic background searches is that even though our data is non-stationary, our pixels remain uncorrelated, at least as long as it's as long as it's quasi-stationary, not too non-stationary. And so, yeah, Neil had a paper about this last year, and we're also looking into that, if those small off-diagonal components in the covariance could change parameter estimation. So the likelihood you get at the end of the day in the WDM domain looks exactly like the normal Whittle likelihood you would get in Fourier domain, but just summed over pixel by pixel. And this WDM transform has a long history in gravitational waves. The coherent wave burst pipeline has been using it for like 2 decades or something. And a lot of people in the room have worked on it as well. Matt Digman has used it for cyclostationary noise before and still origin black holes with Neil. And there's a few reviews. A couple of them just came out, actually. Yeah. So if you have non-stationary PSD, and you want to convert that to a WDM dynamic PSD. This is just an example I made up where there's kind of a sinusoidal modulation in this null frequency here. There's a very straightforward way to do that. You can integrate the PSD against the WDM kernel, the WDM window here. Okay, so that's kind of all the formalism we need to do noise and stochastic background studies in this domain. So the results I'm going to show you guys, I'm taking a cosmological background to be totally stationary in the data. I'm taking a confusion noise to be modulated according to the orbital solution of the satellites and the location of the galaxy. And for now, I'm just pre-computing that modulation and fixing it. And the instrumental noise, we're modeling at the link level. And we're actually taking the individual link level amplitudes to optionally depend on time. For now, I just put in a linear slope. So when you add all these things together, this is like, for example, in the X channel, you can have a ramp in instrumental noise and see the confusion noise changing as well. And I should also mention, we also model the full orbits, how they contribute to the noises as well. So things like those orbital nulls moving around are modeled and tracked as well. So one other thing we do to speed up inference, yeah, in principle, you could just do the straight likelihood calculation on the full data stream. If you have in data points in time, then you have in data points in the WDM domain as well. So you actually end up with a fairly expensive likelihood calculation. So one thing we developed is this, it's a kind of an analogy to Welch's method in frequency domain, where you average over small small windows in time pixels. But the difference by doing it in WDM is we can track the non-stationarity. Yeah, and you know, if you're averaging together a bunch of Gaussian distributed random numbers, that gives you a chi-squared distribution or a gamma distribution. So that changes the likelihood a little bit, but we can do this inference and accelerate the likelihood quite a bit. And we can even take into account the next order correction due to the PSD not being constant in small time windows. This is the Satterthwaite approximation. It's the next order correction to averages of Gaussian variables with different variances. So in this PSD, the correction is only important at the times when the confusion noise is going up and down steeply. Okay, so we can put all that together and try doing stochastic background inference. So here I injected a curve like this red one. The cosmologists in the room will recognize it. Yeah, we can totally inject this with non-stationary confusion noise, do the recovery, and because we're tracking the non-stationarity, we can do a lot better. And it doesn't really matter if we use the full resolution likelihood, that's the blue here, or the coarse range version, that's the red. And this is a model with the non-stationary noise. So the instrument noise is getting, I think in the X channel at least, is getting worse over time. I think in some of the other channels it's getting lower. I just threw all the corner plots on one slide. Don't look at them too hard, but just get the feeling that the non-stationary case is doing well. It's less biased. I'm showing the OMS noises, the test mass noises, and the rates that they're varying. If you look at the galactic foreground parameters, we do a lot better in the non-stationary case compared to the stationary one. And in this case, there's actually a power law stochastic background in there as well, and we can recover it more tightly in non-stationary noise. I've been talking to a few people about this and thinking about it. It's kind of why is non-stationarity better? Why is it helping us out, even though it's like the stationary analysis should give you the same average noise level? One way to think about it is the maximum log likelihood should be something like the SNR squared. And in the stationary case, say we had stationary noise, 2 data points, then you get one value, but if you have non-stationary noise and the noise is a third lower and then a third higher, that time when the noise is low actually weighs really highly and gives you more information. Even if you have the same average noise level, if you have times when it goes lower, those will really, really give you a lot of information. That's pretty much all I had to show you guys at the moment. Hopefully we'll be writing up some of this analysis soon. So WDM in general, is really great way to model non-stationarity. And if you're interested, I recommend one of these recent reference papers that came out. This matches a lot of results that people have been coming out with recently to say that the non-stationarity actually helps your analysis. It doesn't hurt it. As long as you can model it, you should track it. And it's made me think that if we had the choice, maybe it would be good to have a more non-stationary instrument than a stationary one, as long as we could model it. As mentioned, my collaborator Tina is giving a talk about Brownian noise in LISA and non-stationary analysis, very similar to what I'm talking about in another session. And for now, I'm just doing a very simple instrumental model. I'll have to figure out a better one in the future. Thanks.
Okay, thank you very much. Let's go for a non-stationary LISA. Questions?
Hello. Very cool talk, Robbie. I was curious, is there any trend with which parameters seem to improve the most with the inclusion of the non-stationary noise model?
Yeah, good question. Can you see one? I'm not sure I see one. It seems like the noises definitely improve, which makes sense. I guess you're getting more information on them. The foreground improves as well. And this power law backgrounds doesn't change as much. So yeah, I haven't really thought about which one should improve more or less.
Hey, Robbie, thanks for this. I guess I have a very similar question, but I'm going to ask it in a different way to see if you're going to answer differently. Some of these parameters seem significantly more biased than others if you use the wrong approximation. What do you think is driving that?
Yeah. So my guess would be data where there's times when you're in a very non-stationary part of the PSD, it hurts you worse. Like I think Tyson and Neil have been looking at galactic binaries, and if you look at a galactic binary at 2 or 3 millihertz, then it makes a big difference, a stationary analysis or a non-stationary one. But a binary at 5 millihertz, it matters less. Yeah.
Cool, thanks.
Can please Konstantinos Kritos prepare in the meantime?
Yeah, it's not quite what Robbie's doing, but if you, on the case of a templated type search, it's usually the extrinsic parameters that are most affected by non-stationarity, and the intrinsic are less affected. So,
Interesting.
Okay, let's thank Robbie again. Which one is yours? This one?
So, so thank you again, everyone. My name is Konstantinos Kritos, and now we're going to talk about a few of the things that Lisa will see. And in particular, things such as tidal captures, gravitational wave captures, Bremsstrahlung, and tidal disruption events. So, I would like to define the lost cone, which is just this, locus, this set of velocity vectors whose orbit lies within the lost cone. So let's suppose that we have a massive black hole in our nuclear star cluster that we all like, and we have an orbit that passes through some very close to the black hole. Then what can happen is that black hole may be captured by the supermassive black hole, or if it is a star, it may be tidally destroyed. So all of these orbits whose pericenter is within that critical radius, we say that they are in the lost cone. They are lost from. And for example, if you look at the radius of a star that needs to come within a supermassive black hole in order to be disrupted, that is about 2 milliparsec. And stars can be destroyed tidally, and there can be a flare that may be observable. But black holes can do something which is interesting, which is they can actually emit a lot of gravitational waves if they come near the supermassive black hole, and they can be captured. So we've heard about MRIs. These are more like captured orbits, or let's say more direct plunges. So if the black hole comes very close to this supermassive black hole, then what will happen essentially is that the orbit will not go back to infinity as it would in Newtonian mechanics. It will be captured in a very eccentric orbit that merges quickly. How quickly? 28 minutes with these parameters. You have Sagittarius A star, up to factor 4, okay? In 30 minutes, this black hole will harden quickly from eccentricity close to 1, and then it will merge. And it emits a burst of gravitational waves in this process. And the question is, can we see this? The frequencies are right in the millihertz band for these events. Of course, we have to look at rates, how often do we get these captures or these star absorption events. You can do simulations. You can look at loss cone rates. So as you evolve the nuclear star cluster for a Hubble time, you can keep track of what is the solar masses that are accreted every year by the supermassive black hole. And you can do this for all kinds of stellar objects, main sequence stars, giant stars. You can look at stellar remnants such as white dwarfs, neutron stars, and black holes. And you can see that with time, main sequence evolve. So over time, the rate decreases. But in the long term, black hole captures dominate. So we can ask the question, is the background going to be strong enough? And at the same time, we also have white dwarfs and neutron stars. So that's the kind of question we want to investigate. And these are multi-messenger transients. In other words, they don't just emit gravitational waves, or they also emit electromagnetic waves. So this is the disruption of a sun. If the sun comes very close to Sagittarius A star, Sagittarius A star is going to apply a torque into the star. It's going to tidally destroy. Approximately 50% of the debris is bound to the black hole because it's nearly on a parabolic orbit. And the time it takes for this debris to come back is something like, if you apply Kepler's third law, you find it's something like 40 days. So in 40 days, the debris will come back. And you can ask the question, can we estimate an efficiency? And can we estimate the luminosity, let's say, for such a tidal absorption event? And these numbers come out here. So you have 10 to the 43 ergs per second for this kind of event. And then you can look at the population of tidal absorption events. And you can map out in this plot that we've seen on day one, you can look at all these tidal absorption events where they lie in this plane. And here we have the extreme nuclear transients, we have tidal absorption events, core collapse supernovae, all kinds of unknown transients. Here is a good chance to use the app for the abbreviations. And you can see that there are the most massive stars in the nuclear star cluster. These are 100 solar masses, main sequence stars, produce very powerful flares. And of course, as the system evolves, those massive stars evolve off the main sequence, and then with time you have lower luminosity signals. But the timescales, the characteristic timescales of these TDEs is in the hundreds of days for black holes that are 10 to the 7, 10 to the 6, or 10 to the 8 solar masses. So how do black holes form? Of course, all of these transients, the tidal absorption events, and the, let's say, black hole captures, they will contribute to the mass of the black hole. So this is what a simulation of such a cluster looks like when you simulate a nuclear star cluster without the black hole to begin with. You just start with a population of stellar mass black holes in the center. With time, if the escape velocity of the system is high enough, you form a black hole, inevitably. All of these stellar mass black holes start forming. And as the intermediate mass black hole grows with time through these repeated mergers, you get all of these signals that become lower and lower in frequency until they hit the Lisa band. And, the color here is just the redshift. So they would start probably heavy, low mass black holes at high redshift, and then we move to heavier black holes with time. And then you can perhaps realize this scenario at even higher redshifts. And this is one way to form the seeds. So I would like to show you some predictions for LISA. So this is what LISA could see when it flies, which is, this is the population of massive black hole binaries. So essentially, we're looking at cosmological merger trees. So this is the New Horizon cosmological simulation, and we are actually keeping track of binaries that form through galaxy-galaxy mergers, and keeping track of their masses and when they merge and what are their properties, such as at what redshift the merger will happen and what is the total mass of the system. And this is a population of massive black hole binaries that merge in this 16 cubic megaparsec
volume of the cosmological simulation, and almost all of the events are detectable, with the exception of course, when you have two massive black holes or two low mass black holes. When you you can consider different bands to see those. But the bulk of the events tend to be in this nice region of the parameter space where we can observe them with amazing sensitivity, with very high synchronous ratio. So what are the rates? How many events are we going to see? This is a prediction, and what you want to look at is actually the panel, the inset panel, which shows the cumulative numbers of mergers, of massive black hole mergers as a function of redshift. For different flavors of massive black hole binaries, IMBH means intermediate mass black hole and supermassive black hole. So there is a few events every year that happen. Now, most likely all of these are detectable, as I showed before, but these are some of the numbers that we get, and the rate here is really limited by the number of galaxy-galaxy mergers. Here are some of the loss cone rates, going back to now the intermediate mass black hole, disrupting tidally a star or capturing black holes. Here are the numbers. So what you would have to do if you want to find cumulative loss cone rates, you would have to integrate over, let's say, the black hole, supermassive black hole mass function. You have to weight by the number density of supermassive black holes, let's say in the local universe or up to some redshift. These are unknowns. So what I'm doing here is I'm just parameterizing the rate in terms of these unknown quantities. We have some constraints on the number density of supermassive black holes, but if you scale it to 10 to the negative 2 supermassive black holes in every, let's say, cubic megaparsec, then you find that the number of tidal disruption events that occur every year up to a redshift of 6 is about 4 times 10 to the 6. So millions of tidal disruption events. And when you look at the number of black hole captures, so black holes cannot be disrupted, they're not made of a fluid, they can be captured through gravitational Bremsstrahlung, you find 10 to the 4 Bremsstrahlung events. These are not emeries, these are very highly eccentric captures that circularize quickly, and within, I showed before, 30 minutes they merge. Same with the white dwarfs and neutron stars, and now we can ask the question, are these detectable? If not, is the total sum detectable? And before showing you the result, another interesting thing is, can we grow the masses of supermassive black holes solely by TDEs, tidal disruption events, and captures? Or do we need other channels to consider? And the answer is, if you integrate the total mass budget accreted from these channels, it's falling short of Sultan's estimate based on the hierarchy AGN number, but still the tidal disruption events and compact captures, they can contribute to about 25%, up to 25% of the mass of supermassive black holes today. So we need gas accretion, and this is something important. And going back to the question I posed earlier, can we detect them? So I compute the characteristic strain to, this is an order of magnitude calculation, and you can see some different masses here. This is the mass of the supermassive black hole. I placed this at the redshift of 5, let's say a high redshift event. We can probe these now, and most of these are marginally detectable. So let's look at the background. So each event may not be easy to detect and to see individually, but if we sum over all of the events, so here you can see we're going to sum over all the unseen, the undetectable, and here it's you have to make some assumption of what detectability means. It's just going to be an SNR cut, which is an order of magnitude, but these are the backgrounds. So in particular, the white dwarf background is what I want you to look at, is the background. This background is essentially the energy density, the normalized energy density from captures of white dwarfs, and that dominates over everything else. Thank you.
Thank you very much. Questions?
Sorry, thanks, Kostas, for this. I feel like you cut yourself short. Is that because there's just so many more?
There are two reasons. Yes, there is more, a lot more. Of course, they are more massive, so you could think of they have smaller cross-section, right? And they segregate less. But on the one hand, there is many more, and on the second, they don't get any natal kick at formation, like the black holes or neutron stars. So you effectively retain all white dwarfs in the cluster, and so there's much more overall.
How much trouble are we in if that background sticks up where it does for the white dwarfs? Like, that's blending into the white dwarf background in our own galaxy, right?
I think that's in a higher frequency compared to the other background.
So maybe I didn't catch it, but how long did you integrate the polar integrated sensitivity curve here?
Oh, this is scaled to 4 years. Of course, you can put the number, your favorite number here, 10 years, but this background doesn't depend on that because this n would increase.
Okay, let's thank the speaker again. Thank you very much. So as far as I understand, the next talk is by Jonathan Menu, and it is online.
All right, good. Yeah, thanks for the opportunity to talk remotely here today. So my name is Jonathan. I'm going to talk about simulated data generation for Mojito. So Mojito has been mentioned earlier in this session. It's the code name for the so-called common data set 1, in which we're currently working on, and this is a product of the LISA DDPC. So DDPC is an acronym you also may have heard before, but let me position it a little bit clearer for those of you who are maybe not fully aware. So DDPC stands for Distributed Data Processing Center. It is an entity which is organized in different coordination units, and I'm presenting today or representing today the simulation coordination unit. Now, as the spelling of center suggests, with the RE in the end, this is a European, or actually more precisely an ESA member state kind of organization. It has also a counterpart in the US, which is called the NASA Science Ground Segment. And together with the Science Operations Center, which is coming from the ESA project side, they're kind of forming the Science Ground Segment, which is everything related to the kind of scientific organization from a data analysis and a data production kind of or data pipeline point of view, I should say. Now, together, they're interfacing with the science community, so that might include many people here in the audience, and a subset of these people organizes themselves as a LISA consortium. So depending on where you actually are, you could probably fit yourself in one of these boxes. Now, what I'm going to address today is an important problem. The problem that if we are eventually going to switch on LISA detector, we obviously will have quite some trouble to find ourselves. Find our favorite source kind of mixed with many other sources together in perhaps a very noisy data set. And I would say that even if we were for the purpose of the talk, if we had launched LISA 12 years ago and we would get our first actual data set today, we would be very happy. But then soon it would probably turn out that our life is, will be quite miserable because of the kind of messy nature of this data. Now, fortunately for miserable lives, there's always a solution, and the solution could be alcohol. Alcohol in many kind of mixes, many combinations. Now, of course, I'm not suggesting all of you to become alcoholic to deal with this miserable LISA data analysis live. What I really want to give as a message here is that we probably want to look at LISA data as a kind of cocktail of gravitational wave source and noise data. So if you're able to cope with this kind of complex cocktails of these sources and noises, then we'll probably have a good start when LISA will actually be flying in 12 years and when we will be analyzing the data and we'll be having a happy life. Now, the kind of suggestion that comes out of this idea is that, well, when we can produce many kind of synthetic LISA data sets that kind of, well, represent the universe in maybe simplistic ways at first, but then in the most realistic and maybe even more difficult ways than we would imagine. And the kind of approach that we would be using there or should be using there is a kind of following a cocktail recipe, where we basically select the ingredients based on what we think the universe will look like and what we think we can handle at the moment when we start, building our pipelines for this analysis. So, for instance, if you would imagine your kind of first vanilla LISA data set, you will probably have a lot of binary white dwarfs. You have massive black hole binaries, some of which are merging. You may have MRIs, you may have stellar origin black hole binaries like LVK is observing, but then in an earlier stage. You may have maybe stochastic gravitational wave backgrounds. And of course, we shouldn't be forgetting about all our instrumental noises, some of which, or probably most of which, will be non-stationary. Of course, this cocktail ID is not a new ID. Well, in fact, synthetic data sets have been generated for, several decades already for LISA, and it's only like in the late 2010s, the community has started to organize these LISA data challenges, which have been given cocktail names to indicate basically how easy we can cope with them and getting more difficult along the increasing timeline. So at least the first mixes were quite light to digest. So there were few gravitational wave sources in a kind of simple mixture. We had a simplified instrument simulation, and also it was kind of organized as a community activity. Now, since LISA since the mission adoption, there's the formal DDBC entity that started to function, well, together also with the NASA ground segment, of course. Well, we are moving now to these more semi-representative mixture of astrophysical and cosmological sources. We have a much more accurate instrument and response simulation. And then we think about conventions, which is probably a good idea to do. So organized, well, at least under DDBC here. So what is this first data set then? This common data set 1, also known as Mojito. So in this table here, you see an overview of all the sources which we are considering. Now, it's important to stress here that we have two variants of this Mojito data set. There is a light variant, which we kind of have produced last year, or the end of last year, and which is now being analyzed. And there's also a heavy variant, which is under preparation. And as you can see in this table, specifically in the population, specifically in the population column, you see that we, for instance, increase the number of sources, and we also increase the kinds of sources that we actually introduce. So we have galactic stellar binaries, we have extragalactic ones, for instance, including Andromeda LMC for the heavy data set. There's the massive black hole binaries, which we're increasing from 20 in Mojito Light to 100 in Mojito Heavy. There's MRIs involved, and also for Mojito Heavy is that we introduce a couple of stochastic backgrounds, basically. You see the waveforms are mentioned here. Most of these waveforms are publicly available, and we use these to generate our data sets. So if you give just to give a flavor of the sources that we include, here are some of the plots. Some plots of some of the parameters of this Mojito Light sources, or the populations that we assumed. So you see, for instance, mass ratios for the MRIs, mass ratios for the star origin black hole binaries. sky positions of the massive black hole binaries, which are, for instance, well, basically randomly positioned on the sky. And then on the top right, you see the galactic binaries has been mentioned a couple of times already. Of course, over density towards galactic plane and mainly towards the galactic center. And what on the bottom right, you see here, for instance, that we include both positive F dot and negative F dot frequencies.
Jonathan,
sorry, I hear a question from. Okay, sorry.
So you can go ahead.
No, sorry. So there is a sorry, I was saying a positive and negative frequency derivatives, so ones that are governed by gravitational waves only, and then others which are interacting and which are basically have an increasing period. Instrument and response simulation is well, something which we consider in two flavors for Mojito Light and for Mojito Heavy. So we use the standard LISA instrument and LISA GW response tools. For Light, we have included the main noise sources being the optical metrology system noise on the higher frequency side, and then the test mass noise on the lower frequency side. I mean, of course, they're everywhere, but one is contributing on one of the end and the other one on the other end of the spectrum. And then for heavy, we introduce also some non-stationary noises, or actually a couple of them, to kind of increase the level of realism. For the response, we're also considering this time-varying arm length. So this is not anymore kind of a nicely equilateral triangle, but we consider the actual effect on, for instance, the time delay interferometry. These data sets are produced in so-called bricks. So because we assume at this point that response is basically, can be added or is linearly additive, we can produce individual bricks that represent the different sources and the different signals. So individual sources, and then also the noise brick is separate. So this allows you to make your custom mix of for instance, taking MRIs and the galactic binaries, for instance, including or excluding noise, which is all very useful at this early stage where you want to kind of build your pipeline. And then we spent quite some time at the very end of the production on validation. So we have kind of analyzed in detail, all of the features or kind of the usual features that you would expect in these data sets. So we're expecting merger times are fine with our time conventions. We had, for instance, on the left-hand side, you see the different modes of an MBHB that is merging at a given time, and how you can kind of approximate the first order evolution of the F22 mode. There's the MRIs here that are all plotted together with the different plunge times and the many harmonics that are showing up. And then for galactic binaries or for verification binaries, you see, of course, this kind of almost monochromatic signal. But then if you zoom in, you can relate the kind of modulation over time to the antenna pattern, for instance, and the sky location of the source. A final step was that we also did actual comparison with the fast, with the templates basically for data analysis. So we compared the injection with the faster fast waveform and response and fast TDI kind of solutions, just to see which kind of residuals are there and if these are acceptable. And then for some of the sources, we went all the way to parameter estimation to actually confirm that whatever we injected, we're also able to at least recover with the data analysis solutions. So what is next? We have the data analysis for Mojito Light, which is currently ongoing. We expect that later in 2026, we have also a public Mojito Light release. And then we're working at the moment on preparing Mojito Heavy production. So this should be finished early 2027, after which we will also move the data analysis to this new data set. And then finally in 2028, we have the second common data set coming up, which will be Long Island IST. So I guess by the next symposium, there will be an update related to this. So I want to send you home with this message, and it's probably a good one to start the evening with for you. So thanks thanks for being present, and yeah, I'm happy to accept any questions.
Thank you very much. Questions?
Hi, so this is the first I've noticed that the Mojito light and Mojito heavy galactic binary populations have a different number input. Is that because they're coming from different population synthesis runs, or is that because you just downsampled one to make the simulation cost lighter?
Okay, so there's another population which is considered. That's one thing, but also we are also, I mean, in Mojito Light, we were limiting the galactic binaries, at least frequencies, to fall within the strict kind of Lisa band of 0.1 millihertz to 0.1 hertz. Now we're extending this band towards 0.01 millihertz because obviously people are interested in looking also below band, and this seems a valid choice to do. So that's why we're increasing from 15 to suddenly 40 million sources. Yes.
Okay, that makes sense. Just to clarify, so it's the same input population as far as which code, which settings, whatever you believe about common envelope. It's just a different realization, and going to lower frequency is the difference.
Yes. Yeah.
Okay, great.
Any urgent question? We are running a bit late. Doesn't look like, so thank you very much.
Thank you.
Our next speaker is Matthew Digman. Please.
Hello. Hi. I guess kind of following on a theme here, I'm here to talk about my own code involving Lisa Galactic Stochastic Binaries. I think it's been covered in a number of talks, but here we go. This one. So the original, concept for this galactic stochastic code came from a paper that Neil and I wrote a couple of years ago that was using the same iterative fit method that I think most of us are familiar with to analyze the Lisa binaries, but to do it in a method that allowed for a time-varying galactic stochastic background instead of a constant galactic stochastic background. So the reason it's time varying, as you can see, is that the galaxy is extremely concentrated towards the center, and I think that this is obviously very saturated. This is from the LDC data set. I think it's even more concentrated than this makes it look, but you just have to saturate it to even make it apparent that there's much of a distribution at all. But the reality is that the vast majority of the galaxies are in really a few pixels around here at this resolution, in helpix resolution. As Alexander was telling me, the helpix is not an efficient way of representing the galaxy. So we have something like this, and as Lisa's antenna pattern rotates, so it'll come across something like this, whatever, I can't project it into the coordinates right now, but it is a quadrupolar antenna pattern that rotates and crosses near the galactic center twice per year. So you get the dominant periodicity you get in the noise level is at 6 months, and then you get harmonics of that, and if you could see the T channel, you would actually get third of a year harmonics in that, but that doesn't really appear in the other channels. So you have something like this that rotates around a galaxy, and you model the variation correctly. So the current implementation of that is this public code for use by astro people, I guess, mainly. So it takes the paper that we had a couple years ago and turns its methodology into something that has a publicly reasonably usable API, as well as like HDF5 file storage in a way that can produce like traceable results with the provenance of all the configuration parameters known and stuff, so that the results are reproducible across runners and not variable. And so it's using that, and it has a direct interface with the cosmic population synthesis code. Then is I believe popular, so you can take your cosmic galaxy and plug it directly in. This is useful for like astro science purposes because the full global fit is computationally expensive and total overkill for a lot of these purposes, probably. Maybe less, and then like I said, starts the interface. Okay. So I wanted to show like what the kind of signal looks like. So if you ignored the cyclostationary component of, I think Neil had maybe this exact figure, or with an excerpt in his talk, but like a screenshot. But yeah, so you have these waves sort of from the rotation around the galaxy, and then if you don't. If you have a noise model that properly accounts for them, then you almost completely whiten it out, except for a very slight residual. But it pretty statistically is white noise here, although you can, because you know the truth, you can tell it's not. And so then we do the iterative fitting procedure that I think perhaps, well, not this exact figure, but a very similar one was shown before, where we generate the whole galaxy first. And this is by far the most computationally expensive step. This takes like 10 hours currently, which this code started at the LISA Sprint a year ago. And at the time we had scoped the project that getting it any faster than 10 hours was a waste of time. But now with GPU codes, apparently that's very slow. So, but anyway, GPU acceleration to come, but currently this first step takes like 10 hours, and then the whole rest of it takes like a couple minutes. But the first step is co-adding like 100 million galaxies or something into the main waveform, and that's the main computational overhead. And you can see kind of like there's some sources that are detected different, so you can like do analysis like that of like which sources are detected. And the key part for this purpose is that you can run it with completely different galaxies. So what I've done here is, I think these are, I didn't label it, or it's not hardly even tell which is which, but these are, one of these is the LDC data set. I think the purple one is the LDC data set. I'm pretty sure about that one. And then the rest are realizations of cosmic binaries, so the synthesis code. These are apparently used in a number of things. The cosmic realization, these specific cosmic realizations are used for testing for a number of things, and I think like the galactic binary people probably have seen them. Specifically, you can see that they can generate pretty different spectrum. This one is a lot lower amplitude and cuts off a lot of frequency, and then others have either a higher amplitude but a sharper cutoff or whatever. So, and I think all of the, and sorry, I should have said, the top plot I think is 1 year, 2 years, and then maybe 8 years. So this is not like, these are, it gets smoother as you integrate over more time, and with some models, the galaxy is essentially gone after the full LISA is observing, although that's probably optimistic for our purposes, or pessimistic depending on what your favorite science is. But anyway, apparently these population synthesis knobs have enough knobs that you can make like actual, real, meaningful differences in what you see there. And then similarly, you can do the differences in the time variability. I don't think that these particular set of models fully explore the limits of what's possible in terms of the distribution within the galaxy, but you can sort of see the scatter within them. So the cosmic ones, I think, are, so I was correct, the purple one's the LDC because it's different from all the others more so than the cosmic ones, which are relatively clustered, because I think they're using a similar model of the galaxy. But so you can kind of get an idea like that. And as I think Ravi said in his talk, the lows matter a lot more than the highs because this gets cubed when you're talking about like the range or the number of sources Lisa sees. So I guess, so the fact that like this model is really low here increases the range by a lot more than you might think or what. And then you can also do, so this is what I was saying, the variation in the time it takes to fully mitigate the galaxy. So that one particular one is essentially almost 100% mitigated by the end, or like 99.5% maybe. And then the others are perhaps more realistic. And then you can see that. You can also compare what those different galaxies look like in terms of the wavelet domain after subtraction. So you can see like this is I think the same one that cuts off at the lowest frequency, so you can, and this is the LDC one, so you can see like a significant difference in what it looks like in the wavelet domain, like a sharp cutoff versus a more gradual one. Like I said, the performance was excellent a year ago, but apparently now slow. But anyway, the point of this was that you could run hundreds of galaxies feasibly on a single core, and that's a pretty reasonable amount of galaxies for most purposes. And subsequent, and then the parallelization hopefully will be coming soon to make the usefulness competitive, I guess. So the other thing is it can have interfaces for other codes. It has, like I said, the HDF5 files with a specified interface for traceability and whatnot, and then it can convert between different things. For an example of an interface that is also soon to be coming out is a new public code I'm working on called ChirpLag, which lets you generate like tens of millions of realizations of stellar origin black hole binaries and make the histogram of like when they would merge versus the mass. So you could say like, what is the delay time between when Lisa would see it and when like LIGO follow-up would see it. So you can see that for really heavy stuff, I mean, surprisingly, no one, we see that essentially only while Lisa is actually on. That's what the gray dash line here. Whereas for like 10 solar mass stuff, we're only seeing stuff, or the bulk of the stuff we're seeing is maybe 15 years from merger, and then on out to like, I mean, this code is capable of saying if you had a 0.01 solar mass black hole merger, it would be on average 1 million years from merger or whatever, but when it was detected, but that's coming soon. I don't know, if you're like maybe for PVHs for something like that. But like I said, part of the point is that you can interface this code with the GalacticStochastic code as well, so that you can look at how the different galaxy models would affect the rate and like detection characteristics of potential multi-messenger type things. And then that's the conclusions here. So, okay, let's see that.
Thank you very much. Questions?
How long till I can run this on the GPUs, Matthew?
Depends on if Claude is as good as they say, I guess. I don't really know how to write a GPU code right now.
So if I understand correctly, to construct the final galaxy after 4 years, you're not subtracting the sources based on SNR, but you are actually fitting the actual waveform? for each galactic binary? Or?
For this, yes, we're not doing the full global fit. So we're computing the waveform of each individual galaxy, and then we get the SNR of that, and then so we co-add all of them at the start, and then we make a decision about which ones should be excluded on subsequent iterations. And it's our particular implementation, we sort of like converge between adding whether or not to add faint binaries and whether or not to subtract bright ones, and then you just sort of bring them together to like squeeze out to a final distribution of.
Right, so it is based still on just an SNR
It's just an
evaluation.
SNR estimate, yeah. It's not like a full likelihood thing or anything, yeah.
Okay, thank you. Okay, so apologies for being late. Let's thank all the speakers of the session.